Okay, good afternoon, everyone. I hope you are doing all right and ready to review the material that we have covered after the first midterm. And I have brought some slides. Of course, it's not going to be everything in one class, but I have brought some of the main pointers or the main ideas here, okay, for the review. So let's keep that in mind. So let's start by polling on this one. Oh, to poll, I need to start clicker, don't I? Okay, so polling is open. Let's do a minute and 30 seconds for this. Thirty more seconds. So the picture you see here is the a method of using right hand rule to find current in a loop. Five more seconds. Five, four, three, two, one, and it stops. Okay, let's see what we got here. So we got B and D, and there are some A as well, one C. Okay, looks like, depending on which way you look from, this kind of drawing could be a little bit confusing, looks like. Okay, so here, this is closer side, that's what I'm writing. Oops. And this is away from us. So that means the this is like saying, okay, it is left. And that's the convention I'm going to be using for the test as well. So left on the screen, right? And this A, the way I'm drawing here, this is going to be up. So anyway, so here what's happening is current is circulating. This arrow represents the direction of circulation of current. So that means your fingers should be curling and going something like this. So when I do that, what happens is my straight thumb goes on this side. Okay. So my finger, when I bring my fingers, when I wrap my fingers something like this, then my thumb goes something like this. So based on this information, the answer should be B. But I see it is kind of also, I think, okay, this loop orientation. So this is drawn in 2 dimension, and loop being 3 dimension, that could be a little bit confusing, looks like. So that's why I think I'm getting, quite a few of you got D as the correct answer as well. So let me stop sharing, and I have this loop here. And also, of course, there is a diagram that should be good enough to, see it. But let's see if this helps here. So there is this loop. So this loop over here looks like, its current is going like this, circulating like that. So I have to grab this loop with my fingers going in that direction. So thumb is pointing in that direction here. So thumb is pointing to my, I don't know, your side may be switched. Often the camera flips the image. So that's what we do. You grab this coil, or pretend to grab, in the direction of flow of current, and then make sure to stretch your thumb. Okay. Another way to do the same thing is to grab this coil. See how I'm grabbing here? By pointing this thumb in the direction of flow of current. We talked about this method while talking about Ampere's law, and we're going to be talking about that soon as well. So you see my fingers are now pointing something like this. So in this case, now you switch the role of the fingers, okay? So when you grab the coil, you are grabbing with these fingers like this, in the finger pointing in the direction of flow of current. But when you are, grabbing this wire kind of thingy, let's say loop, and then what you are doing is you are grabbing such a way that your thumb points in the direction of flow of current. Okay. So for example, we can have multiple coils like this. So if you are given which direction current is circulating, you can grab something like that. So that's my right hand. If current is going something like that, so into the screen towards you from the top, okay? If it's going other way around, and then we flip that, and now my thumb is pointing opposite direction, see? Okay.
I have a quick question.
Sure.
I'm somehow getting D, like I keep pointing my thumb in the direction of current, but then when I curl my fingers, it's D. So how do I do that again?
So see, I'm showing you these fingers here, right? So you can think of, so it looks like, like which side? This side is close to us, and this the other side, back side of the, so this is one side of the loop, and that is on the left side. Think about something like that, okay?
Dr. Ramesh, we can't see the screen. It's not being shared right now. At
Oh
least,
yeah, I see. Yep. I often forget once we
okay.
share that.
Thank
Okay.
you.
Thank you for reminding. So see, this side of the coil is closer to us. So if I bring back, so this side here, so this, it's drawn something like this, and this side is let's say, closer to us, and looks like that could be also confusing in this case. Maybe I shouldn't give you the coil, something like that. It's slightly different orientation like this. And that way, I guess, wouldn't be that much confusion. But here, what you want to know is, remember is that you have to wrap your finger in the direction of flow of current, and then the thumb, stretch the thumb, and that should give you the magnetic field in that direction. Okay, so do you have something like this? Okay, yeah, grab with the fingers. So whatever direction it's going, so it's gonna depend on. So I see when we have this loop, it could be like, let's say, like yeah, that looks like that could be confusing. I already kind of noticed. So this part of the loop is, let's say, this, I said this was the phase, okay? So loop, let's say this loop is near you, let's say, okay? Here, what I meant was a phase, so I think that is also kind of confusing, okay? So loop itself is closer here to you. Let's think of something like that. I think that's going to be better. So that loop is closer to you. Okay, so when you do that, now your thumb should give you that direction of B. But looks like, yes, you are doing right the way I see you in the video, how you are grabbing. Okay. Okay, anything else, folks? Okay, let's move on to the another right hand rule. So here, this diagram I just grabbed from the note, and I'm trying to explain the same thing here. So what happens is when a charged particle is moving in a magnetic field, so for example here these electrons are moving in that direction, and there is a magnetic field that is into the screen, and into the screen we denote that by drawing cross, right? So that's how the magnetic field is in this case. And this basically shows you how to orient your fingers. So you start first, your finger is straight, just like we had here. First you start something like that, and then you start curling, okay? So now I'll let you do it. And notice this is electron, not proton, or not the positive charge. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. So let's see what we got in this case. So there is a bit more for C. So in this case, if you have two pens or pencils, something like this, orient one in the direction of the velocity, another one in the direction of magnetic field. Okay, and hold that with the left hand. Free up your right hand. Okay, and then now align your right hand in the direction of V. So this is V in my screen. Electron is going to the right, and this is right for me. Okay, but you may be seeing this as my left. It's all my, maybe it's still my right, but the way I'm seeing versus you are seeing maybe a little bit flipped. So now with that, you start with, again, hand like this. Now you have to orient your hand. So see, you need to be able to do this freely. Okay. So start by stretching these fingers in the direction of V. While doing that, also keep in mind that the palm, see, the palm should be facing towards the B so that you can crawl in that direction. Okay. So now here I can even do that without pencil just by looking at the picture. So I am orienting something like that, and then since this is going into, I'm doing that. So it points up, my thumb points up, and that would be for the positive charge. But this being the negative charge, I need to reverse that direction for the negative charge. So that's why it is down. So looks like C is correct answer, just like many of you indicated. Okay, so here I have written the same thing here. This I copied from the, uh, this is in the another slide, but what you have right now, when I have posted, this slide is not there. I just try to make it a bit bigger on the next slide. I just added it, okay? But these things are, in the coming slide as well. So this is what I'm talking about, right? Point your right hand fingers in the direction of V. So in this case, you should be doing this. And since the magnetic field is going into, you should orient your palm into the screen. If it is sitting on the, if you have a paper or tablet is sitting flat on the horizontal surface, that means it is pointing down. Okay, your palm should be pointing down so that you can crawl this in that direction. Okay, so basically these two, okay, are the main thing about right hand rule. So how you orient, just that is the different depending on situation. Okay, so anything you like to add or ask on this one? Okay, then let's move on. So what happens is force, as you saw, although the charge was moving in that direction, force was acting either down. If this was positive, that would be up. Okay, something like that. So force acts perpendicular to the V and B as well. Both force is perpendicular to both V and B. So that's how it works. So since force is acting perpendicular to the V, what happens is the object moves in circular path. So now we can use Newton's law to equate the speed, radius of the circle, and the force acting on it. Okay. So By the way, in this case, let's see if I did that correctly. So if I drew this force correctly here, do you want to practice this? So B is pointing that way, going that way. Magnetic field is coming out of the screen in this case. Dot means out. So here I'm claiming that F is pointing in this direction up in this case. Can you see that? Can you use your hand and confirm that? Go ahead. I'll give you 30 seconds. Use your hand, point fingers in the direction of V, and then palm should be out, pointing out because these fields are coming out here, right? Screen. So, and then crawl fingers, stretch your finger. So it looks like your finger should go down in this case. That's what it is doing. And that would be for positive charge, but this being negative, I have to reverse that. So that's why this is up. And remember, in this case, the direction of V did not change. It was same as what we had in the previous slide, but the magnetic field changed. So magnetic field was going in the previous case. This case, it's coming out. So that's why it makes sense to say, okay, the force is pointing up in this case at that point. Okay. If the electron was there and moving something like that, then you need to point your finger down. So in that case, thumb gonna point that way, and the opposite of that is there. So always the force, this is for positive, but this being negative is gonna point there. So that's why this object just keeps moving. This negative charge keeps moving in circle. If this was positive charge, this would still be moving in a circle, but rather than going something like that, this would be going something like that. Oh, that doesn't look like circle, but you got the idea. Okay. If this was positive charge and moving something like that, and if there was similar magnetic field, then this would be going something like that. So what happens is when we put a charge in a magnetic field, and if it is moving, then it starts moving in a circle. Okay. So that means we can use Newton's second law, just like we did for circular motion. So sum of forces along the radial direction is equal to mass times acceleration. And in this case, mass m and g, mass, and this force of charge is very small compared to this force due to magnetic field. And because of that, we can neglect that. So we can think of, okay, there is just one force is acting. And we learned that force on a charge due to a magnetic field is Q, V, P sine of angle between V and B. Okay, so that angle is angle between V and B. So in this case, for example, B is going this way to the right in the sketch, and field is coming directly out. So the angle between them is 90 degree. Do you see that? So theta is 90 degree because B is on the plane of the screen and B is coming out perpendicular to the screen. So that means the angle between them is 90 degree. So when theta is 90 degrees, sine 90 is 1. That's when the maximum force occurs. And that's the situation here. So I can replace that force by this. And this is the radial acceleration, and radial acceleration is v squared over r. Okay. So now you can rearrange this to solve for anything you are asked to find. Okay. Looks like 1v can be cancelled here because there is v and there is v squared. So that gives us just that. So you can rearrange this for r or m or q whatever you are asked to find. Okay, so that's how you use Newton's second law for charge moving in a magnetic field. And here is situation. There is wire. Hopefully you can see it in this picture. And I'm saying current is flowing up in the wire. Okay. So now it produces circular magnetic field. And magnitude or the value of that field is given by this equation where I is current, this mu naught is a constant magnetic permeability. Okay. I is current in the wire. So what's the difference between current in the previous wire versus this wire? Basically, not much. The way we are looking at here, this is a straight wire. Before we had a coil, okay? We had a coil and current going something like this. Here, this is straight. So you can think of, okay, you open this coil and now it looks something like this. So something like that, okay? Same idea. So coil could be thought as the wire as well. So this forms loop, but that's not visible here. But what we know is now current is flowing up something like that, and that produces the magnetic field, and that magnetic field depends on the current and how far we are looking at. So for example, if the point of interest is here, then R gonna be that because that's the circle we are interested in. If point is here, then R gonna be there, that, and circle gonna be this smaller circle. So it depends on R and I. So larger the I, larger gonna be the magnetic field, but larger the value of R means farther we are from the wire, smaller the magnetic field. Okay, so that's what it is telling us. So magnitude is given by this, and refraction is given by this right-hand rule, where you grab. So if you have pencil or pen with you, I'm sure you do. So you want to grab by pointing thumb in the direction of the current flow, and let fingers crawl. Okay, and that's gonna give you the direction of magnetic field. So I'm opening the poll. You have 1 minute to poll on this. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly D, but there are A, B, C as well. All of them have like 5 choices. Interesting. So the situation is similar to this one here, right? So when you crawl your finger, it's going like that, and that is called counterclockwise, right? So this is counterclockwise. So yes, D is correct answer in this case. If the current was going down, now can you do that? If current was going down, by the way, this is D. If the current was going down, then you would point your thumb down here so that your finger would be curling in the opposite direction, means clockwise. Okay? So this technique is used for the straight wire, but you can use that for the coil as well. Just like I said before, you can use this technique for the coil as well. So if you just look at the small segment of this coil, whole coil, you can think of this as just a wire, straight wire, kind of straight wire, okay? So you can grab it by pointing thumb in that direction, just like we did over here. Okay, so are we good here? So here is another question. So what happens is, before we said, okay, a charge is moving. This could be positive or negative charge moving in a magnetic field. Okay, that's what we said. Now we are saying, okay, there is a wire and current flowing. And we know flow of current is the flow of charges, movement of charge. So it is nothing much different than what we had before. But what we know about direction of current is that we assume that whenever we say, okay, current is flowing that direction, we assume that positive charge is moving in that direction. That's it. Because in conventional current we're talking about, right? So the convention is that the direction of current is same as the direction of positive charge that would move or that is moving. But we know actually it's the electrons that move, but here we're not talking about that. This is whenever we show this current, we mean this is conventional current, and that means it is positive charge that's moving in that direction. So that's how we have to read or understand. Okay. So once we have wire something like this, that means we have, several charges moving. So charge experience force means now wire experience force. So for example, if you were to put a magnet in your pocket and bring another magnet, what happens? It's not just the magnet that experiences force. Now it seems like your shirt is experiencing that force. It's going to get pulled, right? So same thing. There is electron in the wire. They experience the force. Because of that, whole wire experience the force. So why understanding like that is useful? Because we already know what is the force experienced by a charge moving in a magnetic field. We already know that. So now this can be written as this formula by simply replacing B by delta X over delta T, right? So this delta X is equivalent to the length segment of the wire. So that's what that is, okay? And when you pair this time with the current, charge over time is current. So that's how we are getting this equation, okay? So this is force on a current wire. if there is no current flowing, the wire not going to experience force. Keep that in mind. So that's why rather than just saying current, sorry, the wire, we have to say, okay, wire. That would be the better statement. So anyway, so that's the value. Now, how about direction? So to find the direction of force, we use the same technique, okay, that we used here. So now here, rather than saying direction of V, since V is not there, we say, okay, I. So we have that I. So that's what it is saying. Point your right hand fingers in the direction of current. Whole thing like that, right? And then crawl in the direction of magnetic field. So curling is possible when you place or point your palm in the direction of magnetic field. That way you can crawl it. If you flip your hand, then see, you cannot crawl in, right? So that's why your palm has to be pointing that direction. I believe this side is called the palm, right? I'm hoping this is not called palm, right? So now it's your turn. So I'm going to turn on the polling. You have a minute. See, your finger should be going either left or right. That's how the screen is, right? The wire. So current is going this way, so that means your finger should be going left on the screen. And your palm should be pointing. See, the B is out. And by the way, on the test, this out thing not going to be there, just the dot or cross. So you have to remember what dot means and what cross means. Okay. So your palm should be pointing up. Oh, I forgot to warn. Looks like all in. I'm going to be closing in 5 seconds. Okay. 5, 4, 3, 2, 1, and it stops. Okay, let's see. How did we do here? Still there is confusion. There is a bit more for up than B. So when I point my fingers to the left, see the current is going to the left. So I need to point my fingers to the left. And then the palm should be pointing. If you are looking at the vertical screen, then your palm should be pointing towards you because magnetic field is out, means it's coming towards you, right? If your screen is flat on the, let's say, on the table, then your palm should be up, okay? So now curl it. So you are curling up, right? So that means your thumb is pointing up in the screen, up on the screen. So yes, A is correct answer in this case. So this is same as if it was the positive charge moving. Okay, same method, same method. So put your screen, if you made mistake here, I suggest put your screen vertical, okay? Vertical so that I can, screen vertical so that I can, like let's say guide you just in case if you made mistake. So now right hand free, right? fingers going to the left. Why fingers going left? Because current is going left in the screen. See that? Now field is out, means they are coming towards you. If they were arrow, they're gonna hit in your body. They are shooting towards you. Okay. So that means crawl your fingers towards you. You can crawl your finger towards you only if you orient your hand pointing thumb up in this case. Your palm should be, facing towards you. If your palm is facing towards the screen, your thumb is pointing down. Okay? And that would be the case if the field was going into the screen. If the field was going into the screen, then palm should be facing away from you, just like you see my hand. This palm is facing away from me, and thumb is pointing down now. You see that? Okay, so that is force on current and force on the wire, and how to find value in direction. If numbers are given, I'm sure you can just plug in numbers and find the value. And finding direction, for that you need your right hand. Okay. So now, this is about induction. I think motional EMF, that's what we said. So in this case, field is going, so magnetic field, and field is going in. And by the way, field is B and force due to this field is F. Remember, field and force, they are not same. Force is experienced by charge or current in the field. So there is field and it experiences the charge, moving charge or current experience force. So there is difference between force and field. They are not same thing. So that's why field is B, and whenever we have force, I write F, and to indicate it is because of the magnetic field, you may also see B subscript, but it does not have to be. It is a kind of force, and any notation, general notation is F, okay? So now, let's suppose we have a conductor. So conductor is full of charges, right? And if this conductor is moving in this direction to the right, what happens? It's going to experience force. What is the direction of force experienced by positive charges? In this case, A, left, B, right, C, up, D, down, and E, let's say, out of page or screen. That means dot. Okay. So I'm giving you 30 seconds to fall on this. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see what we got here. So it's still a lot of confusion. So free up your hand. Imagine this is vertical so that, screen is vertical so that everyone, is on same page. Imagine, or if possible, make it vertical. Okay. If you have a laptop, you can make screen vertical anytime you like. If you have a tablet like mine, you can, lift it up a little bit and make it vertical. So now B is going to the right in this case. So what should be your fingers doing? Going to the right. And how about palm? The magnetic field is going into the page in this case. See, the cross means into the page. Okay. So your palm should be pointing away from you. Okay, towards the screen. Your palm should be pointing towards the screen. Now crawl your fingers towards the screen, and what direction your thumb is pointing? It is pointing up, right? So it's pointing up. So C is the correct answer in this case. Remember, B and force, they are perpendicular to each other. So many of you thought B is the correct answer, right? But right is the V. V is right. Force is not in the direction of V, never. It is perpendicular to the V. So if you are choosing that, you are missing that point. You could have eliminated B just like that, remembering, oh, force not going to be in the direction of V. Okay. Okay, so with that, so now what happens when it moves, of course? So that's why you see the positive charges are up there. So positive charge is up, negative charge is down, because negative charge experience force down, okay, in this case. And because of this separation of charge, it acts like a battery, okay? Remember, in a battery, what happens? There are positive charges near positive terminal and negative charge near negative terminal. So same thing is happening here. As long as it is moving, there is separation of charge. So separation of charge in a battery is caused by chemical reaction. Over here, it is caused by magnetic field and the motion. Okay. So now it's acting like a battery. So that means there are going to be flow of current because of that. If there is a complete circuit, of course, battery itself not gonna make current flow. If you connect battery to a circuit, a loop current, loop wire, then there are going to be current flowing. So now with that said, I have this question for you. See, the B is going left right now, okay? So here this makes a circuit. Think about this as a battery. So to figure out which is the positive pole of battery, you need to use right hand rule. See, we were able to figure that out here. So similar thing. So free up your right hand and you start pointing your fingers in the direction of V and crawl your fingers in the direction of B, and a stretched finger gives you force on positive charges, right? And that's going to act like a positive terminal of a battery. Then how the current going to flow? So that's what this question is. So you have now a minute to answer this question. Thirty more seconds. And 5 seconds. 5, 4, 3, 2, 1, and it stops. So now let's see what we got. We have A and B, bit more for A, and there is one C here. So now, if you did not do already, or even if you did, how about think this as, vertical screen, and point your fingers to the left and crawl towards the screen, not towards you, but crawl towards the screen. So that means the thumb is pointing down, means positive charge is going to accumulate here and negative charge is going to accumulate there. So that means the current going to flow, start from positive charge. So that's how the current flows. So it starts from positive charge and goes like that. So this is clockwise. Okay, this is clockwise. Clockwise. Anything you like to ask or add here? Still, there are mistakes. Okay, then let's move on. So one way of induction is, by moving conductor. When conductor is moving in a magnetic field, what happens? It induces electric current, EMF, and so on. And the EMF is given by this equation. And by the way, what is the current then? What is the value of current here? Current is EMF over R. So if this one has a resistance R, and then this is going to be VBL over R. Okay. So that's how we can find the value of current and direction of current. So now here, another way to induce EMF or current is to change the flux, magnetic flux. Okay. So we say, okay, the magnetic field, and to denote magnetic field, we can draw lines. Remember, magnetic field, electric field, they are denoted by drawing lines. So if these lines are denser, for example, there are 3 lines here, but compared to that, if there were just 2 lines over there, then we say, okay, it has a stronger magnetic field. Strength is larger. If there are more number of lines passing through the same area in a region, okay? So over here, when we say area, it has to be area of something. So what area? Often that area is determined by either loop or rectangle, wherever the current is flowing, okay? So the area and how much magnetic field strength is where the loop is situated. So the product of that magnetic field, strength, and the area and cosine of angle between them. So far we had, for the force we had sine, but for the flux we have cosine in the equation, okay? And theta, what is theta here? Theta is angle between A and B, where A is area. But how do we figure out area of a loop? So to figure out direction of area of the loop, of course, the area can be found if once we have radius, it's pi r square. But in this case, looks like we need a direction of area. So here I'm showing direction of area. So why direction of area is up here, just like normal to the coil? Why is that? So for that to be definitive, we also have to know which way current is flowing. See, when current flows something like this in a loop, you can use right hand rule like this, grab it, right? So it's flat. So now from the near side, it's going that way. So you see my thumb is pointing up. So that's why that's the direction of A, area. See, it is not on the plane, but perpendicular to the plane is the direction of area, always. And this could be up or down. And this up and down depends on which way current is circulating. Okay. If current is not circulating, that is basically, no use. But when current is circulating, we can tell, okay, it's pointing that way. So by knowing theta, A and B, we know the magnetic flux. So that is the value of magnetic flux, right? So when area or the loop, if it has a radius r, then area is pi r square. If loop is rectangular, for example, something like that, then this could be length, width. So the area is product of length and width. And to find the direction, you have to know whether current is going this way or that way. Okay? Cannot be going both way at the same time. So now here is a question for you. So flux depends on the magnetic field strength, area, and the angle. Okay. So here what's changing? Radius changed. That means area gonna change because area depends on radius. And magnetic field strength. So that means B is changing. So A and B both are changing. So you have to take account of both. So it looks like angle is not changing. Orientation of the loop is exactly same. There is no information about change. So that means we can say, okay, it is same. So with that, what do you think would be the new flux compared to the old one? So you have a minute, maybe minute and 30 seconds for this. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got here. So we got all of them, bit more for A. So how do I do it? So it says radius of the coil is double. So right now, let's say it is R, and R doubles means becomes 2R, let's say. So that means A becomes now A new, let's say, is pi, and 2R, and 2 has to be squared. So it becomes 4 times pi R squared, and this is the old one. So area becomes 4 times larger. When you double the radius, since radius is squared in the equation, you have to square the double. So that's why you pick up this 4. So area becomes 4 times larger. How about the magnetic field? So magnetic field, new magnetic field is half. Okay, so I can just do half. So half times 4, half times 4 is 2. So that's why doubles is the correct answer. Okay, so B new is half of B. So you can say, okay, new flux FB new is B new times A new times cosine theta. So the cosine theta is not changing. So B new means half of old B, and A new means 4 times of old A and cosine theta. So you see we have BA cosine theta, but now we have these factors of 4 because of the area and factor of half because of the field, being halved. We have that 2, and then BA cosine theta. And this BA cosine theta is our good old flux. So that's why new is 2 times old one.
I have a question.
Yeah.
I solved this conceptually. Would that still work for other examples?
So you solved it conceptually, but what concept you used, you did not share with me, so I cannot say whether your concept gonna work or not.
The way I was thinking about it is that it's a direct relationship, and when we increase area, then that means more magnetic field is going to go through.
Right.
That's how I solved it. Would that work for other problems, or should I do it
Yeah,
mathematically?
but more could be double or quadruple, right? Both of these are more. So how do you figure out which one is, right? So for that, you need to say, okay, area is becoming 4 times larger because radius doubled.
Okay.
Okay.
Makes sense.
Okay, so it looks like it's break time already, but I will leave this. Oh, did I choose the answer here? No. So I'm gonna leave to this slide. See, this is finding the direction of induced flux. So we'll talk about that and we'll have question about that. So for now, let's take 5 minutes break. Okay, folks, so welcome back. So this Faraday law gives us how much EMF is induced when the rate of flux change is this. Okay. So there is N, this N means number of turns in the coil. So for example, here, there is this battery connected to a coil. So it supplies current in the coil when this is on, when switch is on. Right now, switch is off. So no current is flowing. That means no magnetic field here. So that also means no magnetic field here. So that's why this needle or the compass needle is not deflected. It's just sitting there. So now what happens? The moment you turn on switch, for example, briefly that needle deflects. So why it does? Because current goes from 0 to high value, means magnetic field increased. So magnetic field increased means magnetic field changed. So when magnetic field changes, what happens? There is change in flux. So even when the current is not changing, there is magnetic field as long as current is flowing. But for a fixed magnetic current, there are going to be fixed magnetic field. So that means fixed flux. Flux is not changing. But according to Faraday's law, the EMF is induced only when flux is changing. So in this example, flux changes only when switch is either turning on or off for that brief moment. If it is off, then no current, no magnetic field. If it is totally on, then constant current means constant magnetic field means flux is not changing. But for this, that changing moment when switch goes from off to on or on to off, at that time current goes from maximum to zero or zero to maximum, means field is changing. So field changing means flux is also changing. And that changing gives you the EMF. So that's what this equation is about. So this phi b is this and how it is changing. So we already saw it can change when B changes, it changes when A changes, or even it could change when theta is changing, or all those combinations. Okay. So in that situation, what happens? EMF induces. Now, EMF induced means if there is a loop, then what we're going to see is there are going to be current circulating at that moment. Okay. So in this setup, that's what happens. There are going to be brief circulation of current here when it is at the moment when you open versus when you close. When it is fully closed, they are not going to be current flowing. And when it is completely open, they are not going to be current flowing here on this side. And remember, this is iron core that directs the flux into this so that there is no loss of flux. So all the fluxes are going there. So that is about the value. Now, how about direction? The negative sign means direction, and it says, okay, the induced EMF opposes the change in flux. Induced EMF opposes the change in flux. So that gives us clue how the EMF going to be oriented or in what direction current going to be circulating. And for that, we have to go through this 4-step process to do it properly. Okay. So although the circulation going to be clockwise or counterclockwise, there is always 50-50 chance. Even if you just remember, okay, it's going to be either clockwise or counterclockwise. But to actually find it out, you have to go through these 4 steps, and they are not that bad. Step 1, just figure out what's the direction of original magnetic field. So in this case, north pole of the magnet is here, means the field line goes like that, means in this loop, where the loop is, field is going or coming towards the loop. So this field is original field, B, right? So that is step 1, which is pointing to the right, let's say at this point. Inside the coil, they are going to the right. See the purple lines you see here? Is that purple? I think so. Okay. So now, know if field is increasing or decreasing. So for example, in this case, the magnet is coming towards the coil because B is shown, it's going something like that. Right? So B is pointing towards that and arrow is there. So that means it's moving in that direction. So it is going closer means flux is increasing. Okay, flux is increasing. Why? Because B is increasing. So flux is increasing. In this case, it is increasing. And it was to the right. So let me write it down here for this particular situation. Okay. And then now determine the direction of the induced magnetic field using the fact that the induced will always oppose the increase or decrease. Okay, here increasing. So to oppose the increase, it has to line up itself in the opposite direction to oppose the increase. If it was decreasing, then to oppose the decrease, what it has to do? It has to line up in the same direction. right? And so if you are trying to help somebody pull something, then you pull in the same direction, right? And if you are not helping, then you do that in the opposite direction. So anyway, in this case, induced gonna be to the left. Why? Because original is right and it is increasing. To oppose that, it has to go in the opposite direction of right, means it has to be left. So now once you know the induced EMF, induced field has to be pointing to the right, just like I have shown here by drawing these lines. Now what you do is, you know the field has to be in that direction. That means in what direction the current has to be circulating. So for that, you start by pointing thumb in the direction of the field you want, and then see which way these fingers go, right? It's kind of reverse of finding the field. So before we found field by lining up this in the direction of current, now we are doing opposite. Means we know field already, which direction it has to be. Then now use the same rule, but this time figure out the current. Okay, so it tells me which way the current has to be circulating, and I'm showing something like this. So can you confirm that induced current you are getting is circulating something like this? Okay, that's what I'm trying to show you. This is step number 4. They are color coded, and I just grab this from the note. So note describe all these steps as well. So now here is a question. So all those 4 steps for your reference I have written here. So now I'll let you work on this, and you have 1 minute and 30 seconds to answer this question. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so let's see what we got. We got kind of all 3 of them. So now let's see how do we do that. Identify the original magnetic field, and in this case it says it's coming out, right? So it's coming out from the screen. So if your screen is vertical, it is towards you, okay? And it is increasing, right? So it says it's increasing. Let's say towards you. Increasing. Determine the direction of induced. So it is increasing. To oppose that, it has to be going that. So that means away from you. And then now, since the field has to be going in, Now you need to orient your thumb so that it is going into the page. So if it is vertical, it is going towards you. So for that, I need to orient myself so that I can point that way and then curve like this. Okay. So based on this, what I'm seeing is the current has to go clockwise. When my thumb is going into the screen, these fingers are going clockwise. Okay. So that's why A is correct answer in this case. Okay, so with that, that kind of wraps up the magnetic field, force, and the right-hand rule. Now let's move to the waves and sound. So looks like there was a message, a direct message. There is direct message that says, how do we know if the original magnetic field is increasing? The magnetic field is increasing. So I think the question here tells us that, okay? So yes, sometimes the magnet may be moving closer or away. Sometimes you may be told, you may be told just like that, okay? Good point. So now, this is a typical wave. So let me start by pulling on it, and you have a minute to answer this question. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see how did we do. So mostly C, that is good. So this is from peak to peak, or from middle to next middle, or trough to trough. They have same length. We call that wavelength. And from mean position to maximum, that's called amplitude, and that is denoted by A. And here V is the speed of this wave that's moving, right? And these are just axes. So did I choose the answer? Yes. So here is scales. So I'll let you pull on this. This whole thing is L, or length of the wire or string. Okay, 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So what we need to remember here is that, see, from here to here is 1 wavelength, means this is half wavelength, and this is quarter wavelength. Okay, so this is quarter wavelength. From node to antinode is quarter wavelength. And that way I can count. So for example, 1 quarter, 2 quarter, 3 quarter, 4 quarter, 5 quarter, 6 quarter, 7 quarter. Okay. So this is 7 quarter of the wavelength. And that is equal to this whole length. Another thing you want to keep in mind is that where it is fixed, there is node, and where it is not fixed, it's, see, there is a ring, so that means it can slide. So this boundary is not fixed. There is antinode. So looks like C is correct answer in this case. So now what happens? The frequency of the sound you hear changes. Either source is moving or observer is moving, or both of them are moving. Okay, so why that happens? Because of this, you know, like let's say source is moving, so because of that, the the waves in the direction of motion gets basically, you know, closer together, so wavelength decreases. Okay, so that means frequency increases on that side there. And that change can be written something like this, or directly positive, negative, and you choose a sign. So often the equation is written something like this, and we can determine whether it's going to be positive or going to remain negative. Same thing is determined by this. Take BS, means this, and BO, that means this. Positive when moving with the wave propagation, right? So for example, let's say in this case, this portion is not moving at all, let's say. So in that case, velocity of observer going to be 0. So that means it's going to be just V over V minus or plus Vs times Fs. Okay. So if observer is not moving. Similarly, if the source is not moving, then we can make that 0 over there. Now, if one of those moving, let's say in this case, source is moving, car is approaching. So let's say in that case, what happens? The car is moving in the same direction, moving to the same direction as the wave is moving. See, wave is coming towards the ear, right? So portion is observing, means the wave is coming towards the portion. So in that case, car and the wave, they are moving in the same direction, means source and the wave, they are moving in same direction, means Bs is positive. So that means this negative sign remains just that. It does not change. Okay. Now, if we look at here, car is now moving away. So wave is coming towards the ear, so that means B is in that direction, but car is moving that way, so Bs is in that direction. So they are in opposite direction. So in that case, what happens? Bs now becomes negative. Okay, so you need to use negative sign for the Bs, means this becomes now positive. Negative and negative, negative times negative becomes positive. Okay, so that's how it works out. And you do the same thing if the portion is also moving. And here is a question for you. And remember, this was the original equation, and that's where the sign changes. We modify that depending on which one is moving and what. So here car is leaving, okay? And the portion is now, although we don't see this in picture, the person follows the car. Okay, so the observer is moving in that direction. And car is leaving means car is moving in that direction, so the source is going that way. And the wave is arriving to the person means this V is in that direction. So you need to identify those first, and that way you can figure out which one is positive and which one is negative. And based on that, you change the sign, okay? So with that said, maybe a minute. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. Oh, we got all of them. So, see the BO opposite to B means it has to be negative. Okay, BS, see B is going towards the person, but car is moving away from the person. So BS and B, they are also opposite. BS is also opposite. Means both of them are negative. So that means that changes this formula, original formula, to positive because both of them are that. Okay, so what happens in this case is person is moving towards that. Because of that, what happens? The frequency increases, it gets added, but car is moving away from the person. Because of that, it decreases. For that to decrease, you need to add and divide by larger number. Okay, so that's another way to look at it, but this is the way to go. Okay. Okay, so now let's move towards the light. A minute. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see how did we do here. To mostly B. Is that correct? So this is angle of incidence. This is incident ray. And this is normal. So angle between incident ray and normal is called angle of incidence. This angle 40 means this angle is 50. And according to law of reflection, we know this angle and that angle are same, means B is correct choice. So now The answer choices are labeled right there. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So this is mirror. So the ray cannot cross the mirror. So full ray line, it cannot be in that direction. So this is converging. So the parallel one comes towards the focus point. So it looks like D is the best choice here. Okay. But quite a few also chose B. See, this being mirror, if this was lens, then it could cross. But mirror has a painted, so light cannot penetrate through the mirror. Okay. So remembering these principal ray, how to trace these three rays is helpful in this kind of situation. Okay. So it passes through the focal point, parallel one, the one that comes from the focus after reflection gonna go parallel. And the one that hits the center, of course, it gets reflected by making that as a normal. Okay, so these two angles should be same. So these are called principal rays. So that is reflection from mirror. And there can be refraction of light when it goes from one medium to another medium, right? And how it goes from one medium to next medium, it depends on refractive indices. Okay. So now here is a question for you. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So before I forget, I haven't included question from the interference and diffraction chapter, the last chapter we went through, okay, last class. So that will be covered in the final, and everything, of course, in the final. Format of the exam going to be exactly same as midterm. There are going to be 30 questions, 70 minutes, and I'll count best 25. Okay. So now for this one, let's see what we got. So slightly more for B, and that is correct answer. So how do we know that? See, it's going from this way, that is indicated by arrow. Now, when it refracts, it's moving, going away from the normal. See, this angle theta 2 is bigger than theta 1. You can see that right there. Okay. If it was equal, would be something like that. If it was smaller, would be something like that. So it's moving away from, means N2 is smaller than N1. Okay. If it was doing something like this, that would mean N2 is bigger than N1. And we know this is also called total internal reflection. So the critical angle can be found by using this Snell's law, where one of the angle on this side has to be 90 degrees. So this becomes 1. So you can solve this for critical angle. So that's how the refraction works. So now for the lenses, for example, so last time we talked about mirror. So here it's a lens. So light refracts through the lens. So what do you think is the correct answer in this case? Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly D, that is correct. So this being lens, what happens? Light refracts. So that means it goes something like that. If it was diverging lens, then it's gonna go like that, and back produced gonna look like this. Okay, so it would go something like that if it was diverging or concave lens. So here is this. Parallel goes through the focus just like mirror, but on the mirror it goes on the same side, but for the lens it goes to the opposite side. And the one that passes through the center goes undeviated, and the one that passes through the focal point on this side goes parallel on the other side. So that's why they look like a kind of opposite of one other, may look like similar line. Okay. So now what happens is we use lens formula to find object distance, image distance, or focal length. So for that, we have to use correct sign convention. So let's see if you remember. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. We got a lot of B and there are some C. Sign of virtual object. Virtual means negative. Focal length of concave lens. Concave lens means this kind of diverging lens. So that means that is negative. Focal length of concave mirror. So concave mirror, on the other hand, is like that. So it has a real focal point. So that means it's a positive. So looks like it is negative, negative, and positive. Oh, looks like You guys need to work on this one bit more. Okay. So here is this table that tells you, see here, virtual object is negative. Okay, virtual image is negative. So whenever you see virtual, that is negative. And this is lens formula or mirror formula. To use this, you need to use correct sign convention. There are quite a few problems done in the note for the mirror and lenses. You want to take a look how they are used and how calculated. And magnification is defined in terms of height or distance. Okay. And now let's see. Here is a question for you. I guess that's going to be last question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got here. And there are quite a few B, but all of them. So looks like there is problem here for the near because it's not focusing on the retina. Not focusing on retina means problem. So that means it cannot see the near. So that's why it is not nearsightedness. Okay, it is farsightedness. It can see just fine. And since the rays of light are going far from the retina, maybe converging lens will help. Okay, so converging lens means convex lens, another name for converging lens. So yes, B is correct answer in this case. And in the slides, I discuss about those, and of course, they are also in the note. And you can also find refracting power by finding 1 over F. And the unit of F has to be in meters for this formula to use. So that's all, folks. So I'll see you next class for the test.
Thank you.
Bye.